So here we go, starting with the day's session. We're starting it with a bang, the supermassive black hole story. Dr. Andrea Ghez has double degrees from Caltech. She is a professor of astrophysics at UCLA, and last year she became the fourth woman to be awarded the Nobel Prize in physics. It was for her work revealing the supermassive black hole lurking at the center of the Milky Way galaxy. What you may not know about her: until she was 4, she wanted to be a ballerina. But when she was watching the moon landing in 1969, that changed the trajectory of her life. And the fact that she made the right choice became clear one morning when her phone began ringing at 2:45 in the morning, an hour when, as she says, anybody's first reaction to the home phone ringing in the middle of the night is, "Everybody okay?" But then very quickly you realize, she said, this is a different kind of phone call. Dr. Ghez, come on down.
Thank you so much, Pat. I'm just thrilled to be here today to share the story of the work that's been recognized. This story actually began when I was finishing my PhD at Caltech, when Keck Observatory was just first coming online. And when I saw those first light images, what I understood then was I wanted a job that would enable me to use these fabulous facilities more than anything else in the world. So I was really delighted a year later to get a job at UCLA, where I could work on developing new techniques for using these incredible telescopes. These telescopes are the largest telescopes in the world. They're co-owned by the University of California and Caltech, and where they partner with NASA. And my interest in developing these new techniques was to be able to pursue and study black holes. The story I'd like to share with you today is how we've been able to demonstrate the existence of a supermassive black hole at the center of our very own galaxy. And this has given us the best evidence today that these exotic objects exist in the universe, and has provided us with a wonderful laboratory for understanding today both the physics of black holes. In other words, how do black holes warp space-time, or how does gravity work near a supermassive black hole, as well as the astrophysics of black holes. What role do the black holes play in the formation and evolution of galaxies? Now, I like to begin these talks with the question, how do you observe something you can't see? Because black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light, so we can't see them directly. So it seems appropriate to first define what a black hole is, and it seems appropriate to show you a completely blank slide. So while they are objects whose pull of gravity is so intense that we can't see them directly, they're also objects whose mass is confined to 0 volume, so they're infinitesimally small. That means that density, which is mass divided by volume, goes to infinity. And in physics, anytime we have a number going to infinity, we call it a singularity, or equivalently, it's a big red arrow that says you do not have your description of the physical world right here. And that is, in fact, what makes black holes so fascinating to study. They actually represent that today in physics, we don't know how to make the world of general relativity, which is what Einstein is so famous for, and describes the laws of gravity, work together with quantum mechanics, which describes the world of the very small things. So black holes are both. They're both things with massive gravity and are infinitesimally small. So when we understand how to make these two fields work together, presumably we'll actually understand what a black hole is. Today, while we can't describe the physical size of a black hole, there is an abstract size that we can associate with it. It's known as the Schwarzschild radius. It's been popularized by Star Trek as the event horizon. So this is the last point at which one can detect light from. So there's no information that goes from between the inside of the Schwarzschild radius to the outside world. But this size is important for another reason, which is every mass has a Schwarzschild radius associated with it. Your cell phone, any other object that you'd like to turn into a black hole. It's the radius at which, if you could compress an object down to that scale, it would be forced to become the infinitesimally small object known as the black hole. And it's because at that point, gravity overcomes all other known forces. Okay, so let's think about where black holes might appear in the universe. And here, it's a very nice story in terms of understanding two very different modes that science works in. So the original black holes, the first ones that we thought of, were identified through theoretical work. In other words, people thinking about how the most massive stars in our galaxy would evolve and their lives. And it was recognized that these stars would end their lives as supernovas, which is what's shown here. This is an exploding, very massive star that started its life off with maybe more 30 times the mass of the sun or more. And as it explodes, the outer parts explode, but the inner parts of the star actually gravitationally collapse to become a black hole that's roughly 10 times the mass of the sun. Now, this was predicted theoretically, and today we have exquisite evidence that these things exist. And most recently, that evidence comes from gravitational waves detected by LIGO, which, of course, Caltech is part of. The story of the supermassive black holes, the ones that I'm particularly interested in, are quite a different story. We call them supermassive because they're very massive. Rather than being 10 times the mass of the sun, they're 1 million to 1 billion times the mass of the sun. And here the story starts off with the observational side rather than the theoretical side. And we suspect that these supermassive black holes live at the heart of galaxies. So this is a picture that's on a very different scale than the one that we just looked at in the last one. The last one was showing a single star. Here we're seeing a collection of galaxies. And if we zoom in just to the top left here and look at the spiral galaxy, each galaxy contains roughly 100 billion stars. Now, this picture of a galaxy was taken with Hubble Space Telescope at wavelengths that correspond to roughly what your eye detects. There's nothing in this picture that gives rise to the notion of the existence of a supermassive black hole. It was actually pictures somewhat like this one that gave rise to that notion. This is a picture of a type of galaxy known as an active galactic nuclei, and its name denotes exactly what it is. Their nuclei or centers are very active. And active galactic nuclei are a small fraction of all galaxies, roughly 10% of all galaxies. I like to call these the prima donnas of the galaxy worlds. And it's because they're real show-offs. This picture at radio wavelengths shows the outflows coming out from the center. Where the starlight is roughly in this region, so it's in the very center. But what we see in radio wavelengths is these jets of emission coming out at tremendous speeds. So we can infer the amount of energy that's contained in these jets. And that directly points to the idea that there is a very powerful central engine at the middle of this galaxy. And in addition to that, this light at the center looks unlike anything produced by starlight. And in fact, it's posited that this is matter right outside the event horizon, moving very quickly, and in fact will ultimately fall through the event horizon. So you can see that here we're actually seeing the dying habits of these supermassive black holes. In the case of these active galactic nuclei, these are black holes that are thought to be really feasting on a lot of material at the center of the galaxy. So that was thought of from an observational point of view, and theoretically, we've had to catch up in terms of thinking about how these things might have formed. In addition, this is pretty indirect evidence for the existence of these objects. But it did give rise to the idea that perhaps all galaxies, and not just the active galactic nuclei, might harbor supermassive black holes at their centers. So the work that I've done with my team, where we're looking for a black hole at the center of a galaxy, our galaxy, is really getting at the possibility of demonstrating that these exotic objects exist. Now, this is a galaxy. It was that one that was up at the top left, zoomed in. And in fact, if we could get outside our galaxy and look back, this is very much what our galaxy would look like. Galaxies, for the most part, are flattened disk-like structures. Our sun and solar system is about halfway out from the center to the edge of the galaxy. It actually lives in one of the spiral arms. And I like to refer to the region, this region where our sun lives, as the solar neighbor, the galaxy suburbs. Everything out where our sun lives is it's low density, it's calm, it's quiet. Which is really in contrast to what's happening at the center of the galaxy. The center of the galaxy, the density of stars goes way up, so it's very crowded regions. Things move very quickly, and every way that you can describe the characteristics of a galaxy get more intense as you get to the center of the galaxy. So astrophysically, it's a really interesting place, but it is where we think a black hole would reside. Now, our view on the center of our own galaxy is an interesting one because, of course, we live in the plane of our galaxy. So this is a nice picture that demonstrates what the plane of our galaxy looks like from the side of Mauna Kea on Hawaii. In this picture, you'll notice there's a band of white light. That is the plane of our Milky Way. And hopefully you'll also notice that there's a band of a lack of light running through the middle, and that's from all the dust. Now, most of you have at least lived in Pasadena at one point and can really appreciate the impact of smog. And the dust in our galaxy is very much like smog in Los Angeles. It comes from dust particles whose size is roughly the size of the wavelength of optical light. And that means it's a very good blocker of optical light. If you go just longward of optical light to the near infrared, the light can actually penetrate this dust. So all the work that I'm going to show you today has been done in near infrared, in particular at 2 microns. And this is roughly where your TV remote control works. All right, to give you a sense of that contrast between what happens at optical wavelengths and near infrared wavelengths, if you think about photons or light packets, in the optical, only 1 out of every 10 billion photons makes it to us. So it's really a blank screen. In contrast, in the near infrared, 1 out of every 10 photons makes it to us. So we can actually see the center of the galaxy. Now, the key to this experiment is to reveal the presence of a supermassive black hole through the gravitational influence of that concentrated mass on the stars that surround the black hole. These stars will orbit the center of the galaxy for the same reason that the planets orbit the sun, due to the gravitational influence of the sun. So each star tells you how much mass is confined within its orbit. So these stars are really the key. So as you recall from the beginning of the lecture, what we want to show is that there's a lot of mass confined within a very small volume. Ideally, you'd like to get within that Schwarzschild radius. So you really want to get as close to the center of the galaxy as possible. So we are inward bound. And this tells you why I was so interested in working with the Keck Observatory. So as I said before, Keck, it's co-owned by Caltech and the University of California, largest telescopes in the world. And they're located on the summit of Mauna Kea in Hawaii. Now, astronomers have been driven to build larger and larger telescopes for centuries. And there are really 2 campaign promises of large telescopes. The first, and the more traditionally one we focus on, is that the larger the telescope, the the more light one collects. And we describe the scale, the size of telescopes by the size of the primary mirror of the telescope. So the larger the mirror, the more light you can collect. You can think about that as the telescope being like a light bucket. So the larger the bucket's opening, the more light you're collecting. So that means that we can see things that are fainter, and in astronomy, things that are more distant are fainter, and therefore you're really seeing earlier into the early universe. So this is a real driver for much of astronomy, but it isn't the driver for this work. It's actually the second campaign promise that is the key to this project. In principle, the larger the telescope is, the finer the detail that you can see. This is called angular resolution. And the analogy I like to make here is if you think about the technique of the painting technique of pointillism, where you paint with dots, the closer you stand to that painting, the better your ability to see the individual dots. So having a large telescope improves in principle our ability to resolve the details of the universe. Now, this second campaign promise has been much harder to achieve than the first. And the challenge is the atmosphere, the Earth's atmosphere. The Earth's atmosphere is great for us. It allows us to survive here on Earth, but it is a complete headache for astronomers trying to study the universe. If there were no atmosphere, each of the bright stars that we're seeing here would be the size of the smallest structures you're seeing dancing around the screen and would be rock solid. It's the atmosphere that makes these stars look like bug splat patterns that are completely, that are changing every tenth of a second. And this is it's quite profound when you think about it. The light that we're collecting here has been traveling from the center of the galaxy to us for 26,000 years. And in the last 30 microseconds, it gets completely distorted. And maybe to put this number in context in terms of the time this light has been traveling to us, when the light is halfway from the center of the galaxy to us, the very first cave paintings were being painted here on Earth. Okay, so I've spent much of my career thinking about and working on techniques for overcoming the blurring effects of the Earth's atmosphere. Of course, in astronomy, we have a lot of different techniques. Hubble Space Telescope gets above it. It allows us to see things clearly, but Hubble is actually a relatively small telescope. Its diameter is 2.4 meters, and here we have a telescope that's 10 meters from the ground. And the kind of work that I'm presenting you today, the benefits go as the diameter to the fourth power. So in other words, it's 4 times bigger. So it's 4 times 4 times 4 times 4, more powerful if you can figure out how to overcome the blurring effects of the Earth's atmosphere from the Keck Observatory. This animation gives you a sense of the power of these techniques. So we go from taking a long exposure, and these are the 5 bright stars that we were looking at, the bug splat patterns. They're actually known as the speckle patterns. If you take a long exposure, you just average over them. And then this animation then just morphs into what we've been able to achieve to see these stars. Now, these stars are the absolute key to this experiment because it's their motion that has enabled us to discover the black hole at the center of the galaxy. It's probably worth pointing out, well, these animations that show what we're doing look so obvious today, but in fact, when we first proposed to do this work at Keck Observatory in 1994, the first program was turned down. And it was turned down because people didn't think that these techniques would work at Keck in the beginning. Even if they did, that we wouldn't see the stars. And even if they did, if we did see stars, that we wouldn't be able to see them move. So there was a lot of skepticism. And I should have pointed out, actually, when I was introducing Keck, that it was quite it was quite rational, actually, the skepticism, because Keck's large architecture was a new way of building telescopes. Rather than having one single mirror, it was constructed through 36 hexagonal segments that are kept well aligned. So for these techniques to work, that the alignment process really had to be in tip-top form. So these are actually the first demonstrations that Keck had actually achieved the performance for building big mirrors out of segmented telescopes. And today, most modern telescopes are built through this design that was so innovative for Keck. Now, there are a lot of, there's been a huge evolution in the technology that we've used to get to the diffraction limit, or to this high angular resolution that we see today. And in the beginning, it was all very passive. We just took very short exposures, and I like to say it was hardware simple or hardware inexpensive, and software complex or expensive. And today we use a technology called adaptive optics, which is hardware complex. And one would have hoped software simple, but in fact, it's also software complex. And it's a wonderful story of technology transfer, because of course the military cares just as much as astronomy about seeing up and down through the atmosphere. So it was in the mid-90s that the adaptive optics was declassified, and our community really benefited from that declassification. This technology depends on us creating bright artificial stars in the direction that we're looking. So we actually shine lasers up into the atmosphere, and it turns out that there's a very small layer of sodium atoms that are trapped up at an altitude of about 90 kilometers, thanks to meteorites that are raining down on us. And we stimulate those sodium atoms in that very thin layer to shine like a bright star with these lasers. And that enables us to make these images. So this is a movie I could watch for quite a long time. It's a fourth of the real estate that we were looking at before, when we were looking at that on off. And this shows how the stars have moved over the last more than 2 decades. So you do not need any fancy algorithm to see that these stars have moved a tremendous amount. And in fact, it really, I should also note that in the beginning, this experiment, we envisioned only a 3-year experiment to just measure the star's motion on the plane of the sky, and to statistically infer the presence of the black hole. So that was what people didn't think would work. But in fact, this technology has worked out so much better than anybody could have possibly imagined, that we've continued and gotten to this point of being able to measure individual orbits, which is a much more powerful demonstration of the mass that's confined at the center of our galaxy. You can probably find my favorite star in the galaxy. Its name is SO2. It's the most powerful one because its orbital period is a mere 16 years. And it's really amazing in astronomy to have something that happens on a human lifetime. If you think about the orbit of the sun around the center of the galaxy, it takes 200 million years to go around. And you're certainly not going to, well, we're not going to live long enough to see that. But we're so close to the center of the galaxy, and there's such a massive object located there that this object has a period of 16 years. So between the period and the size of the orbit, we can figure out the mass. And of course, the size of the orbit tells you the mass, the region that you confine this mass to. Now, what is that? What have we discovered? We've discovered that there's 4 million times the mass of the sun, which in fact people understood before we started this work. But it was confined to a region that's the size of the circle. So there's lots of stars, gas, dust, all sorts of things. And at that time, one couldn't possibly conclude that there was a supermassive black hole at the center of the galaxy. So what this work has done has been to show that that mass of 4 million times the mass of the sun is confined to a volume that's a factor of 10 million times smaller. So that and that region corresponds to the size of our solar system. So if you think about our solar system, which is dominated by the sun, its mass is 1 times the mass of the sun. In the same region, we have 4 million times as much mass. So this has moved the case for a supermassive black hole from a possibility to a certainty by increasing the evidence by a factor of 10 million. And if you think about anything you'd like to increase, my kids would like to increase their allowance. A factor of 10 million is certainly a tremendous advance. That actually happened in a number of stages, as I mentioned to begin with. The first 3 years, which gave us just the motion on the plane in the sky, gave us the first factor of 1,000, and the individual orbits, once we knew that it was worth continuing, gave us an additional factor of 10,000, building to this factor of 10 million. So today, that has provided us with the strongest evidence to date for the existence of a supermassive black hole at the center of our galaxy, but also at the center of any galaxy in our universe. So today, actually moving forward, I no longer believe that, for me, it's no longer about proving the existence of a supermassive black hole, but rather flipping it on its head and thinking about the center of our own galaxy as a fabulous laboratory for understanding both the physics and astrophysics of black holes. And there are a number of things that that's the center of our attention today. And in fact, I would say that while we started this work with a very clear question that we've got a very clear answer to, this project, which is really all about technology-enabled discovery, has opened up more questions than answers. And as a scientist, that I think is really one of the most fun aspects of discovery. So let me start with the story of the astrophysical role of the black hole. When we first discovered or started to announce the results in the early stages, our thinking about the relationship between supermassive black holes and their host galaxies was framed as a question: which came first, the black hole or the galaxy? Somewhat like the chicken or the egg question, which came first? And of course, we had ideas for explaining both scenarios. But what we understand today is that that's simply the wrong framework. And the reason we believe that is that it seems when we look in other galaxies, as other candidate black holes have emerged, the mass of the central black hole seems to correlate incredibly well with the mass of the central component of the galaxy. It always seems to be about 0.1% of that central piece known as the bulge. And the scales are so vastly different that we understand that one can't causally cause the other. And we realize that whatever formed the galaxy had to form the black hole synergistically, and that there has to be some feedback mechanism that keeps the growth of these two disparate objects in sync together over the lifespan of these entities. And at the center of our own galaxy, we have a really unique opportunity to see what's at the center of these, what's in this region. Almost every single prediction one can make about what one should see at the center of the galaxy around the supermassive black hole has been inconsistent with our observations as the technologies have advanced. And again, this is just a delightful part of being a scientist. For me, it feels like being a kid in a candy shop when your observations, these new ways of seeing the universe, are so disruptive. So let me just give you a quick tour of 3 examples of the things that are happening and are driving our work forward. The first one is that the prediction of what we should see in terms of young stars. So the prediction for young stars, and by young, I mean a few million years old. And to put this in context, 1 million years seems a really long time compared to our lifetime, of course. But if you think about the lifetime of a star, a million years is like the if you scale to the lifetime of a star to a human lifetime, these young stars are like the age of these young stars is like a human gestation period. So these really are just baby stars. And these form out of huge clouds of gas and dust that are very large, but very fragile. And black holes are not nice neighbors to these fragile entities, because black holes have the property or the characteristic for a large object of being able to pull more strongly on one side than the other. That's called a tidal force. It's what causes the tides, if you like to surf here on Earth. But this tidal force will, for these fragile objects, has a tendency to pull things apart, or as we call it, we call this process the spaghettification process. And so the prediction should be that there should be no young stars in this environment. This is an environment that's really inhospitable to star formation. And in fact, there were young stars that were known much further away, where the tidal forces are slightly smaller. And it was the existence of these young stars at greater distances that made people quite skeptical about the existence of a supermassive black hole at the start of this project. But today, we're quite convinced that there is a black hole here. And the young stars in this animation or this picture are the blue-green objects. So in fact, they're the most populous kind of stars that we see. So that's mystery number one. I like to call this the paradox of youth. And one important clue has come from studying these stars. The orbits of these stars, actually, as this animation pulls back, you'd see that many of them share a common orbital plane. And it really looks like a scaled up solar system. So we're actually borrowing many of the ideas that come from thinking about how stars are formed and form planetary systems around them. Because the mass of a planet to the central star is very similar to the mass of these really massive stars to the central black hole. Okay, so we're getting hints, although there's still a tremendous amount of debate and lots of different theories that have been proposed to explain this paradox of youth. All right, the second mystery or unexpected result has to do with the old stars. The old stars are roughly 1 billion years old. In this picture, they're the orange stars. The prediction is that there should be a large concentration of old stars, but as you can see that there are very few. And this is perplexing in a way that's quite profound. It turns out that we use this prediction for a concentration of old stars to be created by the existence of a supermassive black hole to try to find black holes in other galaxies. In other words, we look for this concentration as the smoking gun for the presence of supermassive black holes in more distant galaxies. And yet close to home, where we're quite convinced that there's a black hole, there seems to be a dearth of old stars. So what happened? What happened to the old stars that are predicted to be there? And the third mystery, which I do say is actually currently my favorite mystery, is the magenta objects. These are the objects we didn't even think to make a prediction for. These are fascinating objects. These are objects that we can see being pulled apart, what's known as tidally distorted. So we talked about tidal distortion before. These are objects that are on very eccentric orbits. So in other words, they start far away, they come in close. And as they make their closest approach to the black hole, you see these objects going from compact stellar-like objects to being stretched apart, seeing the top layers of the star being stripped off and presumably feeding the central black hole. Today, our best notion, or at least one of my favorite ideas about what's generating what these objects are possibly pairs of stars. And it turns out that most stars do form as twins, pairs of stars that have been driven to merge by the central black hole. When these stars merge, they become inflated. They could become about 100 times bigger than they started. And at that scale, they have the black hole has the power to strip off the outer layers. This is an intriguing idea because it may provide a mechanism or explain a process that may be really important for explaining some of the mysteries that the gravitational wave experiment, like the LIGO experiment, has seen, which are twofold. One, they're seeing stellar mass black holes that are much larger than what were predicted, and that they're seeing the merger happening more frequently than they expected. So to me, it's really interesting that these two very different views of the universe, these two different windows, may be giving us two puzzle pieces that may be helping us put together the larger picture of what's happening in our universe. Now, let me end with a little peek at the tests of gravitational physics that these stars open up. Near a black hole, one expects space and time to become commingled. This is the warping of space-time. If you go to a science museum, you often see the funnel, the gravity funnel, and that is supposed to help us visualize the mixing of space and time that occurs as you approach the event horizon. In this picture, the event horizon is shown as this ring, and at this point, you're getting to the point in which space and time can actually flip. Okay, so we're gonna, these orbits that we have now give us the first direct test of how gravity works near a supermassive black hole. And you need a complete orbit to know the shape of the orbit in order to get a seat at the table to do these first direct tests of how gravity works near a supermassive black hole. And then, in fact, there are two such tests. The first test, which is known as the relativistic redshift, is reached or is possible after you get the first measurement of the orbit and the next time it goes through closest approach. And what you're looking for is you're looking for a signal that tells us how light travels through space and time from the object to us. And while light is both affected by the motion along our line of sight, which is the classical effect, there's an extra term as the star goes through closest approach, really well into that gravitational well, where the light loses more energy because of its need to climb out of the gravitational potential. So this is called the relativistic redshift. This happened in 2018. So for a long time, we were 2018 or bust. There was a 6-month period in which the key observations were possible. And in fact, our observations have shown and confirmed Einstein's ideas of how gravity works using this metric. The next test actually gets more interesting. It's more interesting, in my opinion, because things don't work quite as neatly as predicted. And in fact, this is a somewhat deeper test of gravity. This is called the precession of the periaps, or rather, it's looking at how the object itself is moving through space and time. And as you go through this region where space and time are mixed, this causes the orbit to maintain its shape, but change its orientation. So somewhat like a children's spiral graph toy, it'll just make a Rosetta pattern. And it will make one in a direction. It turns in what's called the prograde direction, in the direction that it's orbiting. And this signal is predicted to emerge after it's gone all the way around, makes its next closest approach. After that, one should start to see the signal. And this signal just gets stronger and stronger as you get to the furthest approach. So we're somewhere in here. And in fact, I can tell you this very definitively where we are. We were actually on the telescope just last night making these measurements. And what's so exciting is, in fact, our early results are showing that this orbit is perhaps moving or precessing in the direction that's opposite what Einstein was predicting. So today, we're in that. To me, this is not publication ready, it's question ready, because at this point, you have to question every aspect of your analysis. These experiments require that you put 26 years of data together in a way that is very precise. And with each successive test, there's more precision that's required of our processing. So the analogy I like to make here in terms of the process, it's like going around your car and kicking the tires to make sure that actually everything holds up well. To make sure that you don't have an accumulation of small errors to give you what appears to be a discovery, but might be an imperfection of your analysis. So stay tuned for more. Along with all of these new observations, we're also making improvements in the technology. One of the key ways in which we're making progress with the technology is that with one laser, you can only correct about 30% of the mistakes that the atmosphere makes for a 10-meter telescope. And in fact, that fraction is going to get smaller and smaller as you go to a larger and larger telescope. So to improve a higher fraction on today's telescope, we're building a system that uses multiple lasers. This is like doing a CAT scan on the atmosphere and will allow us to understand much more of what's going on at the center of the galaxy. And it'll also enable us to mitigate an important technical risk for the next generation of telescopes that Caltech and the University of California are involved in. This is the 30-meter telescope. This is an incredibly ambitious project. It's a collaboration. In addition to Caltech and UC, it has Canada, Japan, China, and India. It is a truly technically challenging, technically exciting, scientifically exciting, and politically fascinating project. Rather than being built of its primary mirror, again, uses a segmented technology just like Keck, but rather than 36 segments that are each about 1.8 meters in diameter, there's the interesting design choice that was made to actually go to half the size. So there's actually about 492 individual segments that compose this phenomenal facility. This next generation adaptive optics is critical if you want to get to the diffraction limit of the 30-meter telescope. If you only launched one laser, you would only correct maybe 1% or 2% of the light. So at this point, it's also probably worth pointing out that what we see today is only the tip of the iceberg. We only see the brightest stars because it's so crowded in this region. Our ability to correct for the atmosphere and the size of the telescope means we only see the brightest stars, and yet the fainter stars are much more numerous. So it's important to recognize that we see the tip of the iceberg and that we can't see a typical star like the sun. And in only seeing the brightest stars, this would be like trying to understand the economy by only being able to see the largest financial transactions and missing all those numerous but smaller scale transactions. So as we move from what we see today, which is shown here on the left, to what we might see with this next generation adaptive optics system on Keck today, in the middle. This should be ready. This is anticipated to be ready within the next 5 years to the 30-meter telescope, where we should be able to see a whole range of stars and much more typical stars like our sun, similar to our sun, should be revealed. Okay, before I end, I just want to make sure I give huge credit to the team that I've been working with for the past 26 years. And in particular, I want to call out Mark Morris and Eric Becklin, and my very first grad student, Beth Klein, is shown here. I should also note that Eric is also another Caltech alum, and he and I shared the same PhD advisor at Caltech, Gary Neugebauer. Eric was his second grad student, and I was his second to last. So there's a tremendous legacy in this program. Today, we're a team of about 30 core collaborators with a broader international collaboration of about 100 as we've stepped up into the role of being a key science case for the development of technology, both at Keck and for the 30-meter telescope. So if nothing else, I hope I've convinced you that there's a supermassive black hole at the center of our galaxy, and that we've opened more questions than answers thanks to the development of amazing new technology. Thanks for your attention.
Thank you, Andrea. And we have questions coming in for Andrea. Reminder that if you have a question for Andrea, please put it in the Q&A box and not in the chat box. And I was very fascinated to hear about the spaghettification process, which will be great news to fans of the flying spaghetti monster. I think they have a new cause here. So let's get to some of the questions from several people. We have Joel, who has not provided an affiliation, but let's see what Joel has to say. He says, what kind of synergies result from having two Keck telescopes instead of just one?
Yeah, the original vision of having two Keck telescopes was to be able to have them work in concert as an interferometer. So to be able to achieve the resolution of a telescope that's equivalent to the separation between the two telescopes, which is about 80 meters. Now you might say, why bother building an even bigger telescope, single dish? And the answer is that since you only have two of them, you don't have the equivalent of a full mirror, and the contrast ratio is really limited. So this was a vision that worked for a few years. And the original vision was to have outriggers around these big telescopes, but those were never built. So today, the power is in having two fabulous facilities. So you have double the time and double the science.
Do you think that all of these observational telescopes are soon going to be moving up into orbit with the Hubble, given perhaps distortions, disadvantages, pollution, and other drawbacks on Earth-based ones?
Well, so we're going to have James Webb Space Telescope launched and in use soon, and that's a 6-meter telescope. So today, while these telescopes on the ground sound expensive, they're still much, much cheaper than launching them into space. And there's a second really important aspect, which is the way we keep these facilities at the cutting edge. In other words, the way we keep them young and innovative is by changing the instrumentation on these telescopes. So today you can change the instruments on a timescale of a decade, but with James Webb, we'll never be able to change the instrument. It's launched and forever out, it's an Earth trailing orbit, and we're not going to be able to get to it. So I think at this scale, we're still better off or continuing to build telescopes on the ground.
Here's a question from Richard, who got his bachelor's in science in '67. He says, so you're saying my cell phone can become a black hole if it's squeezed smaller than the Schwarzschild radius? Is that physically possible? Is there a smallest black hole that is possible?
Yes, if you can figure out how to squeeze your phone down to its Schwarzschild radius, you can turn it into a black hole. And believe me, I would really like to figure out how to do that. It seems like an abstract black hole to me much of the time. Astrophysically, we have these two different categories or two different scales, the 10 times the mass of the sun and the million to a billion. So those are the two types that we have identified in terms of having a mechanism that can produce black holes. And otherwise, we don't know of the existence of smaller black holes.
Avner has a question. If stars generally form as twins, does our sun have a twin that we aren't or weren't aware of?
That's an interesting question, and it's quite possible. And it seems that most stars formed as twins, and many of them just become disassociated from one another. It's unlikely that our sun had a typical companion because the typical scale for the separation between these twin stars is about a third the size of our solar system. And that would really interfere with the formation of our solar systems. The fact that we have such an orderly planetary system around us suggests that we didn't form with a typical companion, and it would have had to be quite far away and quite loose if it existed.
So you can infer that much just from the existence of the solar system.
Yep.
Dan wants to know, Dan from the class of 73, since you're limited to infrared and longer wavelengths, does that affect your ability to perform spectroscopic analyses of the stars orbiting the central black hole to determine their elemental composition?
Oh, great questions. It's in public talks, we tend to show only images, but in fact, an equally important part of our work has been to take spectra, and we have spectra for most of these stars today. You are correct, which is we can only look in the infrared, so it gives us a limited window. But nonetheless, it gives us access. And in fact, it's the primary way in which we've been able to tell the age of these stars. So I kind of jumped to the idea that we do know the difference between a young and an old star, and that's really through the spectroscopic observations. We don't have as good a handle as one would have in the optical in terms of the detailed chemistry, which would be quite interesting to get to. So we've got a lot of information, but some information is missing.
Wayne, who got his PhD in 72, wants to know, what's the competition like between your group and the German group during similar research on the supermassive black hole at the center of the galaxy? Was it stressful, exciting, and did it bring out the best science?
The last part, absolutely. And I guess I should say yes, 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 is the short answer to that. I quite frankly wish I had kept a journal through all of this, because it's the human side of science. I think it's been really helpful to have these two independent groups going after the same things for a number of reasons. There's nothing like competition to keep you on your toes, to know that there's another group going after a similar thing. It's also true that these measurements are hard, and there's a lot of interesting decisions one has to make in terms of how to analyze how to extract the information from the raw data and how to put such a long time baseline of information together. And having these two groups think independently, I think, allows us a bigger diversity of ideas. We are constantly learning from one another. So it's not that we're completely independent, because of course we're publishing papers. So we learn from one another. We are constantly pointing out each other's mistakes. I mean, that's another part, an important part of science, is that you need somebody else who actually can see when you've got a flaw in your argument. And so I think the two groups have really gotten to a much better understanding, thanks to the existence of each other. There have been moments when this has been stressful, and there have been moments when it's tremendously exciting. So it's had it all, actually.
We have the same question from Elton, who got his PhD in 69, and Scott, who got his bachelor's in 78. Do we know what fraction of black hole mass is composed of dark matter?
Okay, so I'm gonna, so black holes are super interesting in the sense that matter really loses its identity. It's the ultimate neutralizer, because the mass has no identity except for the only characteristics that you can talk about with a black hole are the mass, the charge, and the spin. So you can't talk about matter type. Now, it is true that dark matter, and by dark matter, I'm thinking about the stuff that the universe began with, the goo that had fluctuations that gave rise to presumably the formation of the galaxy and the black hole. So one might imagine that was the initial mass that went into forming the black hole. And then it's continually being built up of matter that's falling in. You can ask about how often stars might fall into the black hole, and that's another useful thing. I mean, one, we should recognize there's no danger to us. We're out here in the suburbs, really far away. And only one out of a star falls into the black hole roughly at a rate of roughly once every 10,000 years. And as you get closer to the black hole, presumably, you may become much more dark matter dominated. So in other words, the growth of the black hole may be strongly affected by that presence of dark matter. The other thing that the dark matter may do is actually alter the appearance of these stars. People have thought about, do dark matter infused stars look different at the center of the galaxy because of that concentration of dark matter? And it might cause things to look a little off compared to stars out here in the suburbs.
Elizabeth, who got her PhD in '97, says, it looks like you're examining spiral galaxies. Are you also able to examine elliptical galaxies?
So in the way that we're doing this work, which is to look at individual stars, our galaxy is the only way we can take this approach. Our galaxy is the only galaxy in which you can measure individual stars orbiting the central black hole. And that's simply because the next closest galaxy is 100 times further away. So we just don't have the ability to see the scale, the small enough scale to do this kind of work anywhere else.
Jody, who is Caltech by way of marriage to Ruben, who got his degree in '70, says, how do you put the third dimension of motion back into your images, given that the motion's probably not in a plane?
Great question. There's actually two ways. So when you have images only, which is all we had in the first decade to tie into that other question about spectroscopy. So for a decade, we only had images, and images alone can do it because you have the dimension of time. So in orbits, you have conservation of angular momentum, which means that these orbits sweep out equal areas in equal time. And the only way so that you can use that to tell the projection of the orbit. It's also true that the spectra allows you to measure the motion along your line of sight, which is your other access to that third dimension. So it's through time and spectroscopy that we get that third dimension.
Tyler, who got his master's in '86, wants to know, do you see gravitational lensing as objects get near the black hole?
Oh, another great question. So it's something that we've actually been...
Of course, they're great questions.
Yeah, love the questions. We've been looking for the signal of gravitational lensing. It's another area that's very... It would be so cool if we could see this, both from the black hole, because it's yet another confirmation from a very different angle, as well as you might look for stellar mass black holes around the big black hole through through lensing events. The prediction, if you just model what we should be able to detect, assuming that you know what's at the center of the galaxy, and of course, as I've shown you, almost every prediction is inconsistent with what we see. So these models or these simulations can be quite wrong. With Keck today, you wouldn't expect to see lensing. That doesn't prevent us from looking. So we haven't seen anything today. But as we advance our technology with this next generation adaptive optics and TMT, we should, the 30-meter telescope, you should get to the point where we should be able to see these lensing events. So it's something that we have high hopes for in the future.
Mark, who graduated in '81, says, is there consideration for the possibility of building a ground-based telescope on Earth's moon? So you have a compromise between the freedom from atmospheric distortion we were talking about and accessibility compared to the space telescopes like the Hubble.
Yep, there have been that idea has been thrown out there, and it's interesting to ask. What drives the choice? I think there's both money, but there's also this is my assessment of it. There's also ties to aerospace industry. So doing this in a satellite form has more synergy than putting something on the moon. So I think that's in part why this telescopes haven't been built on the moon. I mean, there are two reasons: expense and then the synergies.
Abhishek would like to know whether stars around supermassive black holes can sustain planets.
Oh yeah, planets around stars. So we in this talk, we've talked a little bit about tidal forces. So if you think about a planet orbiting a star, those tidal forces very easily pull the planets off. So you could imagine forming them, but they would be really quickly pulled away from the host star.
Vitali, who is a Caltech parent, says this might have been answered by the animation, but it seems that stellar orbits don't share a focal point. Is that true? Is there a reason for it?
Oh, they do. I mean, so the two-dimensional animation that I showed, there's one thing that's deceptive in 2 dimensions because you're looking at the orbits in projection. So the black hole isn't at the focus of the projected ellipse. It's at the focus of the 3-dimensional ellipse. But in projection, it looks like they don't share it. But that's just an optical illusion.
Here's a question from Avner and John. It sounds like the beginning of a sci-fi movie. Do black holes drift at all? Could they launch out of the galaxy independently of surrounding stars? It doesn't seem like it's possible based on your animations, but that could be due to your corrections.
Oh, but not so crazy. Okay, so remember we have these black holes that seem to be tied to the mass of the galaxy. As you go to smaller and smaller galaxies, the smallest galaxies appear to lack black holes. And one idea for that is that they might have formed black holes but couldn't hold on to them. In other words, that as these galaxies have interactions, they can get little kicks. And if the galaxy isn't massive enough, it can't hold on to them. So not so crazy.
You better get the screenplay underway here. Here's Chris, who wants to know whether your observations tell us something about the phenomenon of Hawking radiation. For example, have you seen any evidence that the black hole is evaporating right before your eyes?
So Hawking radiation is this fascinating idea that the black holes can lose energy or matter, and we can't. It's actually incredibly small for the larger black hole, the scale of astrophysical black holes. So that's not something that we can see directly.
Carol, who is Caltech by way of being married to Paul, who was graduated in '72. How do you calculate the spin of a black hole if you can't see it?
So it should impact the orbits. So in fact, it's one of our hopes for the 30-meter telescope is to be able to get to the point where we see, so as we were talking about the precession, there's a term on the precession that's presented by the spin of the black hole. So that's one way that you should see the spin. In terms of calculating the spin, the black hole, it has a range from 0 to the maximum rotational speed that a black hole can have, and one might imagine that the spin of the black hole holds some imprint of how it was formed. In other words, or built up. Was it formed from mostly gas? Through a slow process, which might create a black hole that's not spinning tremendously fast versus a lot of massive merger events, which might make it spin more quickly. So that's one of the reasons that people are interested in measuring the spins of the black hole.
Before I get to the last question, a lot of you in the audience have wanted us to remark on the fact that Jerry Nelson, Caltech class of '65, was a primary inventor of the segmented mirrors used in the Keck telescopes and a pioneer of adaptive optics.
Yes.
No, please go ahead.
Just Jerry was masterful. I mean, a great, not only a brilliant scientist, but also just a huge supporter of everybody who was using it in the early days.
And our last question is from Noreen. Can the new discoveries of the black holes lead us to changing our views on how the universe works?
Say that one more time. I did.
Rewriting the rule book on how the universe works because of the new discoveries about the black holes.
Can we rewrite I mean, I guess I would say that since galaxies are the basic building blocks of the universe, it's incredibly important. It's an important ingredient to ascertain the presence of a supermassive black hole. Our simulations of the universe have assumed that that's in place. So, in some sense, our ideas are in front of our proof. So we're catching up and validating some of the ideas about how a key ingredient in terms of how the universe evolves.
Andrea, thank you very much for being here. Thank you all for your questions. We want you to come back for the next session at 10:25. It's about AI, but then your phone told you that already. Thanks. We'll see you then.